Welcome to the Chapter 2, Part 2 screencast for Chem 1A at Shasta College. This screencast will deal with ions and ionic compounds. Recall that in the periodic table, elements are organized according to their properties. If we look at a particular column or group in the periodic table, we find that the elements in that column or group have similar properties to other elements in that column or group. So the elements in column 1, group 1, the alkali metals, things like sodium and lithium and potassium, have similar chemical properties. They react in a similar way. They form compounds of a similar formula. Same thing for the alkaline earth metals. Same thing for columns 13 and 14 and 15 and 16 and the halogens, column 17, and the noble gases, column 18. They all have elements within a given column that behave similarly to the other elements in that column. Now let's look at a representative example of something that happens in this way. The element sodium, which here is represented three different ways: the word sodium, a picture of sodium metal, and a representation, kind of a simplistic representation of a sodium atom. And if we combine that with chlorine, and chlorine is a sort of green colored poisonous gas, and here is a simplistic representation of a chlorine atom, what ends up happening is a vigorous, violent reaction occurs, lots of heat and light is given off, and if we let the reaction products cool and settle out, what we get is a white powder. Now, what's going on in this reaction is we start with sodium atoms, which have an equal number of protons and electrons, and in fact they have 11 protons and 11 electrons, and that reacts with chlorine atoms, which also have equal numbers of protons and electrons, in this case 17, and what occurs is this outer electron, shown in red here on the sodium atom, is actually transferred from the sodium atom to the chlorine atom, leaving the sodium atom with only 10 electrons, therefore an imbalance in charge. It has one less electron than it started with, therefore it's no longer neutral, and since electrons are negatively charged, the overall, what used to be an atom, is now positively charged. And we call this a sodium ion, and we put a little right superscript of plus to indicate that this is now positively charged. And then when the electron is transferred from sodium to chlorine, now chlorine has one more electron than a neutral atom would have. That makes the chlorine negatively charged, and we represent that by putting a negative superscript on the right, and this would be called a chloride ion. And then the positively charged sodium ion and the negatively charged chloride ion attract each other, and that's the basis for forming this new compound, sodium chloride. Now, in general, ions are atoms, like we saw in the previous example, or they could even be groups of atoms that have either gained or lost electrons and therefore have an overall charge. And because elements in a given column have similar properties, and actually the reason they have similar properties is they have similarities in their electronic structure, more on that down the road, the elements in a given column tend to form ions of the same charge. The alkali metals all form positive 1 charged ions. The alkaline earth metals form positive 2 charged ions. If we jump kind of to the other side of the periodic table, the halogens on the almost farthest to the right column form negative 1 charged ions. Chalcogens tend to form negative 2 charged ions. Pnictogens, less reliably, but they tend to form negative 3 charged ions. The elements in column 13 tend to form positive 3 charged ions. And the elements in group 14, you can see we're kind of in between the ones that form positive and negative, and they usually don't even form ions at all, but for example, carbon can form a negative 4 charged ion. And then the transition metals are kind of a mess. They form positive ions, but there's variable possible charges, and that's very tough to predict. More on that in a little bit. but we're not going to deal with predicting charges for those because that's just too challenging. Now, one other thing to note is the noble gases don't form ions at all. They're not reactive. They are very difficult to form compounds, very difficult to have them gain or lose electrons. And this is actually part of the basis for why the periodic table is arranged the way it is, and part of the basis, or a lot of the basis for why reactions happen the way they do. And that is because the noble gases are very unreactive. And the reason they're very unreactive is they have very stable electron arrangements or configurations the way they are just as elements. And many elements will readily form ions either by gaining electrons or losing electrons, and they will gain electrons or lose electrons until they end up with a stable, quote-unquote, noble gas configuration. So, for example, fluorine, by gaining one electron, ends up with the same number of electrons as neon, stable. Chlorine, same thing. All the halogens gaining one electron make them stable, having an electron arrangement like the noble gases. Elements in column 16 need to gain 2 electrons to be like a noble gas. Column 15 need to gain 3. And on the other side of the periodic table, the alkali metals need to lose 1 electron and form positive 1 ions. Alkaline earths need to lose 2 electrons and form positive 2 ions. So this is going to be a very valuable rule for us. Now, when that happens, when ions are formed, the positive ions, and they happen to be called cations, and the negative ions, the name we use for those are anions, they attract each other and they combine in ratios that give an overall neutral compound, and we call the type of compound ionic because it's made up of ions. Here's an example of a representation of the ionic compound we just talked about, sodium chloride. The green spheres represent negatively charged chloride ions. The purple spheres represent positively charged sodium ions. They attract each other. Positive 1 balances out negative 1, and so it's overall neutral. And then we have positive and negative ions attracting each other in all directions. And there's no, we're highlighting one unit here, but there's no really separate units. It's just a big three-dimensional array. So let's do a couple examples. First of all, one we've already seen. Sodium combines with chlorine to form sodium chloride, NaCl. We've already seen this, but just as a recap, sodium forms a positive 1 charged ion. Chlorine forms a negative 1 charged chloride ion. Positive 1 and negative 1 balance off just nicely, 1 of each, and so the formula is NaCl. But what if our compound is one made when magnesium reacts with fluorine? Well, there's magnesium. It's an alkaline earth metal. It will tend to lose 2 electrons and form a +2 charged ion. Fluorine, like chlorine, is a halogen. It's going to tend to gain 1 electron and form a fluoride -1 charged ion. The positive 2 magnesium ion, the negative 1 fluoride ion do attract each other, but they don't balance out charge-wise. However, if there's a second fluoride ion, then the 2 ions together provide a charge of -2. That balances off the charge of +2 from the magnesium ion, and that gives us an overall formula for magnesium fluoride of MgF2. Okay, one more. How about if lithium combines with nitrogen? Well, lithium is also an alkali metal like sodium. It forms +1 charged ions. Nitrogen is in column 15 or group 15, and it forms -3 charged ions. These will attract each other, but the charges don't balance unless there are just enough positively charged lithium ions to balance off a negatively charged, the -3 charged nitrogen ion, and so that would give us Li3N, or lithium nitride. It's worth noting that ionic compounds usually form when a metal combines with a nonmetal. So we have sodium, a metal, with chlorine, a nonmetal, magnesium, a metal, with fluorine, a nonmetal, or lithium, a metal, with nitrogen, a nonmetal. Now, how do we name these ionic compounds? It's good if we're all speaking the same language. And we have some simple rules for naming ionic compounds. Here we're going to do binary ionic compounds. In other words, ones that have just two elements. At least we'll start with that. And we write the name of the metal first and the nonmetal second. The metal name, we just leave it the way it is. The nonmetal's ending of its name is changed to IDE, so chlorine becomes chloride. And we don't use prefixes. So let's try a couple examples. What if we combine calcium and bromine? Well, calcium is going to make a +2 ion. Bromine is going to make a -1 ion, so we're going to need two of those. So the formula will be CaBr2. And we would call that calcium bromide. The calcium stays the same. The bromine changes to bromide. And you might need to refer to a periodic table to make sure you get all the charges right. Let's try another one. Aluminum with oxygen. Well, aluminum is going to tend to make a +3 charged ion. Oxygen will tend to make a -2 charged ion. And it's going to take 2 +3s to balance off 3 -2s. So the formula is Al2O3. And then the name is aluminum oxide. Aluminum, the metal, is written first. Oxygen, the nonmetal, is written second, but oxygen changes to oxide for naming purposes. Okay, now the next step in ionic compounds is we have to recognize that there are some compounds that have groups of atoms that have overall charges, and those things are called polyatomic ions. Now, there are lots and lots and lots of polyatomic ions. Here's a table that shows at least some of them, and if you become a chem major, you will get very familiar with lots of polyatomic ions. But for the purposes of this course, the ions that I am highlighting here, so nitrate, NO3-, carbonate, CO3-2-, sulfate, phosphate, hydroxide, acetate, and bicarbonate, as well as the positive ion ammonia, those 8 ions are ones that we're going to expect you know without having access to any sort of resources. So yeah, these are ones we'll use often enough. You need to memorize them. So you'll need to know the name and the formula, which includes the number of atoms of each type and overall charge. So let's try a couple examples. What if we are given a compound and we know its name is sodium sulfate? What would its formula be? Well, from the periodic table, we predict that sodium will form a +1 charged ion. Hopefully remember, but at this point we look up that the sulfate ion is SO4 with an overall -2 charge. It's going to, of course, take 2 of the sodium ions to balance off 1 sulfate ion, and so the compound's formula will be Na2SO4. How about magnesium nitrate? Well, magnesium we predict will make a +2 ion. We can tell this from using the periodic table. Nitrate, if we don't remember it, we're going to have to look it up, but nitrate is NO3 with a -1 charge, and it's going to take 2 -1 ions to balance off 1 +2 ion. So we would write this as Mg parentheses NO3 with a subscript 2 after that. So we have 2 of the entire NO3 ions. This grouping has to be put in parentheses to clarify that that's a whole grouping and that we have 2 of everything that's in there. And also note, once we put the formula together, we don't show the charges. Now let's come back to the transition metals, those sort of messy elements in the middle of the periodic table that don't have a very predictable charge of ion. How do we deal with them? Well, for naming purposes, what we do is we indicate the charge of the ion with a Roman numeral. And let's look at an example. Let's say iron, which commonly forms the +2 or the +3 charged ion. It can form other ions as well, but those are the most likely. And what we would do if we're talking about the iron 2+ ion is either write the formula Fe with a superscript +2, or we would call it iron Roman numeral 2 ion. And then, of course, iron 3 would be Fe3+, or iron Roman numeral 3 ion. And that's it. So a little practice with this. What would be the formula of copper 2 chloride? Well, copper Roman numeral 2 means it's a +2 charged copper ion. Chloride, you know, is going to be -1 just from the periodic table, so CuCl2. How about tin IV oxide? Well, Roman numeral IV means 4, so it's going to be a tin 4+ ion. Oxide is an oxygen ion, which will be a -2 charge, and it takes 2 -2s to balance 1 +4, so SnO2. Sn is tin. And what would we call FePO4? Well, now you've got a polyatomic ion that you have to recognize, the PO4, and PO4 has a -3 charge overall. That means the Fe has to have a +3 charge overall or on it, and so we would call that iron Roman numeral 3, and then phosphate is PO4. And that's it for the Chapter 2, Part 2 screencast.